Okay, welcome back, ladies and gents. Topic 2.5, the last part of the Lewis dot diagram video series, when we're going to look at resonance structures. Resonance structures, ladies and gents, are basically different ways of drawing the same valid Lewis dot diagram. Or in other words, the electrons can resonate or move within the molecule to give us different structures, but still yet with the same chemical properties and chemical composition. So what is an example of a resonance structure? Let's take a look at this first example with nitrate. You can see that the double bond is on top right here. We very easily could have written this same structure with the double bond down here instead, and then this negative oxygen up here instead. Okay. Or in other words, essentially what we would have done is we would have resonated or moved this pair of electrons into the double bond, and then move this double bond up here to make two more electrons up here. This is what the new structure would look like then. We would now have the double bond here, and the formal charge around that oxygen, if you calculated it, would have been 0. We moved the pair of electrons that was the double bond originally here now up onto the top of this oxygen, and if you calculate the formal charge, it will be negative. And then we left this oxygen alone, didn't do anything to it, and the nitrogen still stayed positive. Now, if we go through and calculate the total charge on it, we still have a -1 charge, because -1 plus +1 cancels, and then we have just the one negative remaining, and then there is yet another -1 Lewis dot structure. It is the same structure, it's just the double bond moved. Okay. We could have also instead put the double bond down here. Okay. Or in other words, what we would do is we would resonate or move these electrons into the bond to make a double bond, and then move these two electrons of this double bond back on top of this oxygen here. And then our new structure would look like this. This would now have a formal charge of -1 if you calculated it. This one would have a formal charge of, I made a mistake there. This one would now have the double bond. This one would have the -1 charge, and then this one would have stayed the same because we didn't touch this one. This is now positive still. Okay. And again, same structure, the double bond is just located in a different place. On a test or quiz, if you were to ask to draw all the resonance structures, you wouldn't have to show the pushing arrows like I did right here. I'm just showing you different ways of thinking about how the electrons move. You would just simply need to show the 3 different ways or the 4 different ways a resonance structure is valid. Now, in truth, if we were to go down to the molecular level and try to actually see these atoms bonding, we would actually see a blend of all 3 of these Lewis dot structures, okay? Because electrons are mobile and they're constantly moving within a molecule, sometimes the double bond will be here, sometimes the double bond will be here, sometimes the double bond would be here. But in truth, that double bond is actually distributed amongst all of the atoms. And now you only need to know that conceptually, you don't have to draw it on the AP exam. But in higher level chemistry, if you go to college to study it, the way to draw this Lewis dot diagram would therefore be the 3 attached oxygens to the central nitrogen, and then drawing a dashed double bond that is distributed amongst all 3 oxygens, okay? With the formal charges still present, with their lone pairs. And overall still with a -1 charge. Once again, you will not be asked to reproduce this on the AP exam. You just need to know that conceptually, electron resonance distributes the electron density across all atoms as equally as possible. But we can only draw it in 3 separate ways. Okay, so you will be asked to produce this up here, not this down here. Okay, let's look at sulfate now. Another thing to keep in mind about resonance structures is you want to try to distribute the charges as equally as possible. Okay. Sulfate, as you know, -2 charge, and then we have these 4 oxygens surrounding it. Okay. There's another way we could draw this. We could actually move one of these into here to make a double bond, and we could do it for another oxygen as well. Let's try to move 2 pairs into the bond here and see what effect this has on the charge on sulfur. Okay, so by doing this, we now have 2 double bonds here, and then we didn't do anything to these 2 oxygens here. Now let's calculate the formal charge for the things that we did change. If you calculate the formal charge for these 2 oxygens, you'll see that they're 0. And any time for the history of chemistry, whenever you see an oxygen double bonded to something and it has 2 lone pairs on it, it's going to be a 0 formal charge. But for the sulfur, we know that sulfur normally wants to have 6 valence electrons. How many are in its vicinity right at this second? Oops. Well, there's 1, 2, 3, 4, 5, 6. Hey, look at that. We completely eliminated the formal charge on the sulfur there. And then we only have the 2 negative charges on the oxygen. If you can eliminate formal charges and distribute the negatives more evenly across the entire molecule, the better your resonance structure is. Okay, this right here is probably a more valid resonance structure because we've eliminated the positive charge on sulfur, which is a nonmetal. And remember things about nonmetals, they either want to be neutral or negative. Okay. Over here it was positive. It could still exist like that, but it's not very likely. This is more likely since it's neutral. And then these 2 nonmetals are negative. Okay, so it takes us back to the concept that nonmetals like to be negative or neutral, and that metals like to be neutral or positive. Okay, so this right here probably is the more valid structure, but there's another way we could have written this instead. Instead of the 2 double bonds being on the sides here, we could have them on top and bottom. So in other words, that would be conceptually moving this double bond here, or moving that pair there, moving this pair here, then taking these 2 double bonds out. Again, on the AP exam, you do not have to show the arrow pushing. You just need to show the rewritten diagrams. And if you go through and calculate the formal charge on sulfur again, you'll still see that it's 0. And that is all you need to know about resonance structures, ladies and gents. It's just, can I draw this a different way such that the structure is still valid? And everybody has their 8 if they need it, or if they're hypervalent, they really don't have any more than 10 or so. Or 12 in this case. Okay. Some of you might be wondering if I can move this double bond into here and this double bond into here, and that way the structure would look like this. And then the formal charge around that sulfur there would be -2. It might be possible for that to happen, but that's an extremely hypervalent sulfur there. And might be a good idea to probably not show it that way, especially since the whole negative charge is concentrated right here in the center on that sulfur, and it's not more spread out like it is over here across two oxygens. Alright, that is all I have for resonance structures, ladies and gents. The AP exam is pretty good about giving you a structure where there's really only maybe 2 or 3 different ways to draw it. There won't be really any more than that, and they're pretty easy to figure out. So go ahead and try the practice problems, and then that will do it for this section. We'll see you in 2.7.